process of determining fault current involves a couple of key steps. Firstly, calculate the full load amperage, abbreviated FLA. Secondly, calculate the prospective short circuit fault current. For step 1, the formula to be used is full load amperage equals kilovoltamps divided by the quantity of volts times 1.732. Now, for step 2, the formula to use is the fault current equals the full load amperage multiplied by the quantity of 100 divided by Z, where Z is the impedance value expressed as a percentage. To illustrate with an example, imagine a three-phase system with the following parameters. The kilovolt amps is equal to 115.5. The voltage is 480/277 volts. The impedance abbreviated as Z is equal to 3%. To calculate the full load amperage, we apply the formula. Full load amperage equals 115.5 divided by the quantity of 480 times 1.732. Performing the calculation, full load amperage equals 0.1452 amps. To calculate the fault current, we use the formula. Fault current equals 0.1452 amps multiplied by the quantity of 100 divided by 0.3. The result is that the fault current equals 484 amps. The impedance value, C, needs to be converted from a percentage to a decimal by dividing the percentage by 100. For example, 3% becomes 0.3 in the calculation. It is vital to use the correct formula to find precise fault current values. Understanding the formula ensures accuracy. Firstly, the per unit impedance is a way to normalize impedance values across different voltage and power levels in an electrical system. Secondly, it simplifies calculations, especially in complex systems, as it removes the need to refer impedances to a common voltage base. Thirdly, it allows for easier comparison of impedance values of different components in the system, regardless of their voltage or power ratings. Fault current calculations are essential for electrical system design and safety for several key reasons. 1. Protection coordination. Fault current calculations are crucial for selecting and coordinating protective devices such as circuit breakers and fuses. Accurate fault current values ensure that these devices can quickly and effectively interrupt fault currents, preventing damage to equipment and minimizing downtime. 2. Equipment ratings. Electrical equipment, including transformers, switchgear, and cables, must be rated to withstand the maximum fault currents they may experience. Fault current calculations help engineers select equipment with adequate short-circuit withstand ratings, ensuring the safety and reliability of the system. 3. Arc flash hazard analysis. Fault current calculations are a critical input for arc flash hazard analysis, which is used to determine the potential severity of arc flash events. By calculating the available fault current, engineers can assess the risk of arc flash and implement appropriate safety measures, such as personal protective equipment and engineering controls to protect personnel. 4. System stability. High fault currents can cause voltage dips and instability in the electrical system. Fault current calculations help engineers assess the impact of faults on system voltage instability, allowing them to design systems that can withstand fault conditions without experiencing cascading failures. 5. Code compliance. Electrical codes and standards, such as the National Electrical Code, abbreviated NEC, require fault current calculations to ensure that electrical systems are designed and installed safely. Compliance with these codes helps to minimize the risk of electrical hazards and ensure the safety of people and property. 6. System upgrades and modifications. Whenever an electrical system is upgraded or modified, fault current calculations should be performed to ensure that the existing equipment can handle the new fault current levels. This is particularly important when adding new loads or changing the system configuration. 7. Troubleshooting. Fault current calculations can be used to troubleshoot electrical problems, such as nuisance tripping of circuit breakers. By comparing the calculated fault current with the actual tripping current, engineers can identify potential problems in the system and take corrective action. To understand the per-unit system, consider the following. The per-unit system is a method of expressing electrical quantities such as voltage, current, impedance, and power as a fraction or a decimal of a chosen base value. It simplifies calculations, particularly in power systems, by normalizing values across different voltage and power levels. To convert a value to per unit, you divide the actual value by the chosen base value. For example, if you have a voltage of 13,800 volts and choose a base voltage of 13,800 volts, the per unit voltage is 13,800 volts divided by 13,800 volts, which equals 1 per unit. Similarly, if you have an impedance of 10 ohms and choose a base impedance of 100 ohms, the per unit impedance is 10 ohms divided by 100 ohms, which equals 0.1 per unit. Choosing appropriate base values is crucial for the per unit system to be effective. Base values are typically chosen to be convenient and representative of the system being analyzed. For example, in a power system, the base voltage might be chosen as the nominal voltage of the system, and the base power might be chosen as the rated power of a transformer. Once the base values are chosen, all other quantities are expressed as a fraction or a decimal of these base values. The per unit system has several advantages in power system analysis. Firstly, it simplifies calculations by normalizing values across different voltage and power levels. Secondly, it allows for easier comparison of values, as they are all expressed as a fraction or a decimal of a common base. Thirdly, it reduces the likelihood of errors, as the units are dimensionless. The per unit system is widely used in power system analysis for tasks such as load flow studies, short circuit studies, and stability studies. It is a powerful tool for simplifying calculations and improving the accuracy of results. The formula for converting actual values to per unit values is as follows. Per unit value equals actual value divided by base value, where actual value is the value of the electrical quantity in its original units such as volts, amps, or ohms. Base value is the chosen base value for that quantity. The base values are typically chosen based on the system's nominal voltage and apparent power ratings. Base impedance equals base voltage squared divided by base apparent power. Base current equals base apparent power divided by base voltage. In a three-phase system, the base apparent power is usually the three-phase apparent power, and the base voltage is the line-to-line voltage. The per unit system simplifies calculations by normalizing values across different voltage and power levels. This is especially useful in power system analysis, where you often have components with different voltage and power ratings. When working with transformers, the impedance is often given as a percentage. This percentage is the per unit impedance expressed as a percentage. To convert it to a per unit value, divide it by 100. For example, if a transformer has an impedance of 5%, the per unit impedance is 0.5. When performing calculations in the per unit system, you can treat all quantities as dimensionless numbers. This simplifies the calculations and reduces the likelihood of errors. After performing the calculations, you can convert the results back to actual values by multiplying the per unit values by the corresponding base values. Consider a 10 megavolt amps transformer with a voltage rating of 13.8 kV/4.16 kV and an impedance of 5%. Choose base values. Base apparent power equals 10 megavolt amps. Base voltage on the high voltage side equals 13.8 kV. Base voltage on the low voltage side equals 4.16 kV. Calculate base impedance. Base impedance on the high voltage side equals 13,800 volts squared divided by 10 million volt amps, which equals 19.44 ohms. Base impedance on the low voltage side equals 4,160 volts squared divided by 10 million volt amps, which equals 1.7306 ohms. Convert the transformer impedance to per unit. Per unit impedance equals 5%, which equals 0.5. Now, you can use these per unit values in your calculations. If you calculate a per unit current, you can convert it back to actual amps by multiplying it by the base current. Firstly, determine system base kilovolt amps and base kilovolts. Choose a convenient kilovolt amp space for the system, often the rating of the largest transformer or generator. Choose a kilovolt space that matches the system voltage level at the point of calculation. Secondly, convert component impedances to per unit values. Obtain impedance data such as transformer impedance, cable impedance, and motor impedance from equipment nameplates or manufacturer's datasheets. Convert all impedances to per unit values based on the chosen kilovolt amp space and kilovolt space. Use the appropriate base values for each component's location in the system. Thirdly, draw the impedance diagram. Represent the electrical system as an impedance diagram, showing all components and their per unit impedances. This diagram helps visualize the system and identify the path of fault current. Fourthly, simplify the impedance diagram. Combine series and parallel impedances to simplify the diagram. This reduces the complexity of the calculations and makes it easier to determine the total impedance to the fault location. Fifthly, calculate the total per unit impedance to the fault. Starting from the fault location, calculate the total per unit impedance back to the source. This involves adding up all the per unit impedances in the fault current path. Sixthly, calculate the per unit fault current. Use the following formula to calculate the per unit fault current, which is equal to base kilovolt amps divided by the square root of 3 times the base kilovolts divided by the per unit impedance. Seventhly, convert the per unit fault current to actual amps. Multiply the per unit fault current by the base current to obtain the fault current in actual amps. The base current is calculated as the base kilovolt amps divided by the square root of 3 times the base kilovolts. Eighthly, consider system voltage factors. Adjust the calculated fault current for voltage factors such as voltage drop and voltage rise, if necessary. This ensures that the fault current calculation is accurate under actual operating conditions. Ninthly, verify results. Compare the calculated fault current with typical values or industry standards to verify the accuracy of the results. If the calculated fault current seems unusually high or low, double-check the input data and calculations. Tenthly, apply safety factors. Apply appropriate safety factors to the calculated fault current to account for uncertainties and variations in system parameters. This ensures that protective devices are adequately sized to interrupt the fault current safely. Firstly, consider the transformer impedance. Transformer impedance is a critical parameter in fault current calculations, as it limits the amount of current that can flow during a fault. The transformer impedance is typically expressed as a percentage of the transformer's kilovolt amps rating. Secondly, consider the cable impedance. Cable impedance also plays a significant role in fault current calculations, especially in long cable runs. The cable impedance depends on the cable size, length, and material. Thirdly, consider the motor contribution. Motors can contribute to the fault current during a fault, as they act as generators immediately after the fault occurs. The motor contribution depends on the motor size, type, and speed. Fourthly, consider the system grounding. The system grounding method, such as solidly grounded, impedance grounded, or ungrounded, affects the magnitude and characteristics of the fault current. Fifthly, consider the voltage level. The voltage level of the system affects the fault current, as higher voltage systems tend to have lower impedance and higher fault currents. Sixthly, consider the source impedance. The source impedance, which is the impedance of the power source feeding the system, also affects the fault current. A lower source impedance results in a higher fault current. Seventhly, consider the fault location. The location of the fault in the system affects the fault current, as faults closer to the source tend to have higher fault currents. Eighthly, consider the fault type. The type of fault, such as a three-phase fault, a phase-to-phase fault, or a phase-to-ground fault, affects the magnitude and characteristics of the fault current. Ninthly, consider the protective devices. The characteristics of the protective devices, such as circuit breakers and fuses, affect the fault current, as they interrupt the fault current to protect the system. Tenthly, consider the coordination of protective devices. The coordination of protective devices is essential to ensure that the correct devices operate to clear the fault while minimizing the impact on the rest of the system. To calculate the symmetrical fault current, follow these steps. Firstly, gather system data. Collect data on all relevant components in the electrical system, including transformers, generators, motors, cables, and overhead lines. This data should include impedance, voltage, kilovolt amps ratings, and connection configurations. Secondly, establish base values. Choose appropriate base values for voltage and apparent power for the system. These base values are used to convert all component impedances to per unit values. Thirdly, convert to per unit. Convert all component impedances to per unit values based on the chosen base values. This simplifies the calculations and allows for easy comparison of impedances. Fourthly, create an equivalent circuit. Create an equivalent circuit diagram of the electrical system showing all components and their per unit impedances. This diagram helps visualize the system and identify the path of fault current. Fifthly, simplify the circuit. Simplify the equivalent circuit by combining series and parallel impedances to reduce the complexity of the calculations. Sixthly, calculate the total impedance. Calculate the total per unit impedance from the fault location back to the source. This involves adding up all the per unit impedances in the fault current path. Seventhly, calculate the fault current. Calculate the per unit fault current using the following formula, which is equal to 1 per unit divided by the total per unit impedance. Eighthly, convert back to amps. Convert the per unit fault current back to actual amps by multiplying it by the base current. Ninthly, adjust for voltage factor. Adjust the calculated fault current for the voltage factor, which accounts for the difference between the nominal voltage and the actual voltage at the fault location. Tenthly, consider X to R ratio. Consider the X to R ratio of the system, which affects the magnitude and duration of the fault current. A higher X to R ratio results in a slower decay of the fault current. For asymmetrical fault current calculations, follow these steps. Firstly, determine the fault type. Determine the type of fault, such as a single line to ground fault, a line-to-line fault, or a double line to ground fault. Secondly, determine the sequence impedances. Determine the positive, negative, and zero sequence impedances of the system. These impedances represent the system's response to unbalanced currents during a fault. Thirdly, create a sequence network. Create a sequence network diagram of the electrical system showing the positive, negative, and zero sequence impedances. Fourthly, interconnect the sequence networks. Interconnect the sequence networks according to the type of fault being analyzed. For example, for a single line to ground fault, the sequence networks are connected in series. Fifthly, solve for sequence currents. Solve for the sequence currents in the interconnected sequence networks. This involves applying network analysis techniques, such as mesh analysis or nodal analysis. Sixthly, calculate phase currents. Calculate the phase currents from the sequence currents using the appropriate transformation equations. The transformation equations depend on the type of fault being analyzed. Seventhly, calculate fault current magnitude. Calculate the magnitude of the fault current in each phase. This involves taking the absolute value of the phase currents. Eighthly, determine maximum fault current. Determine the maximum fault current, which is the highest fault current among all phases. This value is used for selecting protective devices and evaluating system performance. Ninthly, consider the DC offset. Consider the DC offset component of the fault current, which can be significant in some cases. The DC offset component is caused by the asymmetry of the fault current waveform. Tenthly, verify results. Verify the results by comparing the calculated fault current with typical values or industry standards. Also, check that the calculated fault currents are within the interrupting ratings of the protective devices. Transformer impedance is typically expressed as a percentage on the transformer nameplate. For example, a transformer may have an impedance of 5%. This means that the voltage drop across the transformer at full load is 5% of the rated voltage. Transformer impedance limits the fault current that can flow through the transformer during a fault. The higher the transformer impedance, the lower the fault current. Transformer impedance also affects the voltage regulation of the transformer. Higher impedance transformers tend to have poor voltage regulation. Cable impedance depends on the cable size, length, material, and construction. Larger cables have lower impedance than smaller cables. Longer cables have higher impedance than shorter cables. Copper cables have lower impedance than aluminum cables. Cable impedance is typically expressed in ohms per unit length, such as ohms per foot or ohms per kilometer. Cable impedance limits the fault current that can flow through the cable during a fault. Cable impedance also affects the voltage drop along the cable. Higher impedance cables tend to have higher voltage drops. Motor contribution refers to the current that motors contribute to a fault during a fault condition. When a fault occurs, motors act as generators and feed current into the fault. The motor contribution depends on the motor size, type, speed, and distance from the fault. Motor contribution can significantly increase the fault current in a system, especially in industrial facilities with many motors. Motor contribution must be considered when calculating fault currents for selecting protective devices. System grounding refers to the method of connecting the neutral point of a power system to ground. The system grounding method affects the magnitude and characteristics of fault currents. There are several common system grounding methods, including solidly grounded, impedance grounded, and ungrounded. Solidly grounded systems have a direct connection between the neutral point and ground. This results in high fault currents during ground faults, but it also allows for fast clearing of faults. Impedance grounded systems have an impedance, such as a resistor or reactor, connected between the neutral point and ground. This limits the fault current during ground faults, but it also slows down the clearing of faults. Ungrounded systems do not have a direct connection between the neutral point and ground. This results in low fault currents during ground faults, but it also makes it difficult to detect and locate ground faults. The voltage level of a power system affects the magnitude of fault currents. Higher voltage systems tend to have lower impedance and higher fault currents. This is because the impedance of transmission lines and transformers decreases as the voltage increases. Higher voltage systems also require higher interrupting ratings for protective devices. Source impedance refers to the impedance of the power source feeding an electrical system. The source impedance limits the amount of current that can flow into the system during a fault. A lower source impedance results in a higher fault current. The source impedance depends on the type of power source, such as a utility grid, a generator, or a transformer. The fault location affects the magnitude of fault currents. Faults closer to the power source tend to have higher fault currents than faults farther away from the power source. This is because the impedance between the fault location and the power source is lower for faults closer to the power source. The fault type affects the magnitude and characteristics of fault currents. There are several common fault types, including three-phase faults, line-to-line faults, single line-to-ground faults, and double line-to-ground faults. Three-phase faults are the most severe type of fault, and they result in the highest fault currents. Line-to-line faults result in lower fault currents than three-phase faults. Single line-to-ground faults and double line-to-ground faults result in even lower fault currents, but they can still be significant. The protective devices are used to protect electrical systems from damage caused by faults. Protective devices include circuit breakers, fuses, relays, and surge arresters. Circuit breakers and fuses are used to interrupt fault currents and energize the faulted circuit. Relays are used to detect faults and trip circuit breakers. Surge arresters are used to protect equipment from voltage surges caused by lightning or switching operations. The coordination of protective devices is essential to ensure that the correct devices operate to clear a fault while minimizing the impact on the rest of the system. Protective device coordination involves selecting and setting protective devices so that they operate in a specific sequence to isolate the faulted circuit. Protective device coordination also involves considering the time current characteristics of the protective devices to ensure that they operate quickly enough to protect the equipment but not so quickly that they cause nuisance tripping. To calculate the fault current contribution from a motor, you need to consider several factors. Firstly, the motor subtransient reactance, abbreviated as X''D. This represents the motor's impedance to the initial rush of fault current. Secondly, the motor's rated kilovolt amps and voltage. These values are used to calculate the motor's full load current, which is needed to determine the fault current contribution. Thirdly, a multiplying factor, typically between 1 and 4, is used to account for the motor's contribution to the fault current. This factor depends on the motor's type and size. Fourthly, the system's base kilovolt amps and voltage. These values are used to convert the motor's contribution to a per unit value. The formula for calculating the motor's fault current contribution is as follows. Motor contribution equals multiplying factor times full load current. The formula for calculating the motor's full load current is as follows. Full load current equals motor kilovolt amps divided by the quantity of the square root of 3 times motor kilovolts. The formula for converting the motor's contribution to a per unit value is as follows. Per unit motor contribution equals motor contribution divided by base current. The formula for calculating the base current is as follows. Base current equals base kilovolt amps divided by the quantity of the square root of 3 times base kilovolts. Once you have calculated the motor's per unit contribution, you can add it to the other per unit fault current sources in the system to determine the total fault current. Always consult the motor manufacturer's datasheets for the most accurate values of subtransient reactance and multiplying factors. The multiplying factor accounts for the fact that the motor's initial fault current contribution is higher than its full load current. The base kilovolt amps and kilovolts should be chosen to be consistent with the rest of the system. The motor's contribution should be added to the other fault current sources in the system at the motor's location. This is typically done by adding the motor's per unit contribution to the per unit impedance of the system at the motor's location. The total fault current is then calculated using the total per unit impedance. The method of calculating fault current relies on the symmetrical components method, which decomposes unbalanced fault currents into 3 symmetrical components, namely positive, negative and zero sequence components. The positive sequence components represent the balanced 3-phase currents that flow under normal operating conditions. The negative sequence components represent the unbalanced currents that flow due to faults or unbalanced loads. The zero sequence components represent the currents that flow in the neutral conductor or ground due to ground faults. The symmetrical components method simplifies the analysis of unbalanced faults by allowing the fault currents to be calculated using symmetrical network analysis techniques. The symmetrical components method also provides valuable information about the nature of the fault, such as the type of fault and the location of the fault.